single, pretty fascinating source. A detailed analysis called the electron as a standing wave.
Sounds intriguing.
Yeah, and our mission, really, is to try and grasp this fundamental idea the source presents. You know, the electron, this tiny thing we usually picture like a little ball, a particle.
Right.
It completely shifts gears inside an atom. It behaves like a wave. And crucially, how this wave thing isn't just some weird quantum quirk. It's actually why atomic energy levels are fixed. Quantized.
Exactly. Forget the simple picture of electrons orbiting like planets. The source really asks you to visualize something, well, much more abstract.
More abstract, but hopefully clearer in the end.
That's the goal. Electrons acting like stable, vibrating wave patterns, but in 3 dimensions. It's a totally different way of seeing them.
Okay, so let's try and unpack this. The starting point for the analysis, and really for all of quantum mechanics, is this mind-bending idea. Wave-particle duality. What does the source tell us this actually means for something like an electron?
Well, the source puts it pretty plainly. Wave-particle duality means everything, electrons included, shows both wave-like and particle-like properties.
So it's not either.
No, exactly. It's not either a wave or a particle. It behaves like one or the other, or shows aspects of both, depending on how you interact with it or measure it.
And the classic proof the analysis points to is the double slit experiment, right?
That's the one.
Sending electrons through 2 tiny slits, even one by one, somehow still creates that interference pattern you'd expect from waves.
Yeah, like light waves or water waves. It's incredibly counterintuitive if you're only thinking particle.
Absolutely. So how does the source use that?
It uses that experiment to introduce the idea that when we're not measuring it directly, the electron exists as, well, what's called a probability wave.
Meaning it doesn't have a precise spot.
Kind of. It's not like a tiny billiard ball with a definite location. Its behavior is described by this thing called a wave function, which basically tells you the probability of finding it somewhere if you were to look.
Okay, probabilities. But here's where, for me, it gets really interesting. This wave idea isn't just for electrons flying free.
No, not at all.
The analysis stresses that this wave nature is fundamental to understanding electrons bound inside an atom.
That's the crucial connection. Inside the atom, its wave function sort of settles down, takes on a very specific stable form.
And that stable form is what the source calls the standing wave.
Exactly. That's the core concept we're diving into, the electron as a standing wave within the atom.
So how do we get from a changing probability wave for a free electron to a stable standing wave inside an atom? The source brings in Schrödinger's equation from 1926.
Ernst Schrödinger. His equation is, well, it's a fundamental equation. It describes how a quantum system's state, its wave function, changes over time.
But the source mentions a simplification.
Yes, for systems where the potential energy doesn't change over time, and an electron feeling the steady pull of a nucleus is a pretty good example. We can use a simpler version.
Ah, the time-independent Schrödinger equation.
Precisely. And the solutions to that equation, the mathematical shapes of the electron's wave function inside the atom, often written as psi of Mar.
Yes.
Those are what we call the static wave functions, or stationary states. Or, the things chemists usually call atomic orbitals.
Okay, stationary states. Now, my first thought is the electron stops moving. But the source says that's wrong.
Yeah, that's a really important distinction the analysis makes, a common misconception. They're called stationary, not because the electron itself is frozen, but because the probability density, the likelihood of finding the electron at any particular point in space that stays constant over time for these states.
So the pattern is fixed.
Exactly. The source explains it's calculated from the square of the wave function, which for these stationary states just boils down to Barrett. The overall shape of the probability cloud doesn't change, even if the electron itself is, well, we can't really say how it's moving in there in a classical sense. It's the probability distribution that's stationary.
Okay, got it.
Yeah.
A fixed probability pattern. Sure.
Yeah.
How does that connect to being a standing wave? The source uses an analogy, doesn't it?
It does, a really helpful classical one. Think about a guitar string.
Okay. Fixed at both ends.
Right. You pluck it, waves travel down, hit the end, bounce back, and they interfere with the waves still coming.
And sometimes they line up just right.
Exactly. At specific frequencies, the resonant frequencies, you get these stable patterns, standing waves.
Where you see nodes, points that don't move.
And antinodes, points of maximum vibration. The wave pattern itself looks like it's just oscillating in place.
And the key thing for the string, the constraint, is that only certain wavelengths fit perfectly, right? Like An exact number of half wavelengths have to fit between the ends.
Absolutely. If you try to drive it at a frequency where the wave doesn't fit neatly, the reflections just cancel it out. Destructive interference.
So only specific frequencies, specific notes are allowed.
And this is where the analogy really clicks for the electron, as the source points out. The electron's wave function inside the atom is also confined. It's stuck or fixed by the electric pull of the nucleus.
Ah, so the nucleus's pull acts like the fixed ends of the string.
In a way, yes, it provides the boundary conditions. So just like the string only allows those specific standing wave patterns that fit,
The electron's wave function can only exist in specific, stable standing wave patterns that fit inside the atom.
that's it. That's the fundamental insight from solving the Schrödinger equation. These stable, allowed patterns are the orbitals.
And that's why energy is quantized. Because the wave has to fit.
Precisely. The requirement that the electron's probability wave fits within the atom without destructively interfering with itself means only certain wavelengths are possible.
And wavelength is related to energy in quantum mechanics.
Directly related. So only those specific wavelengths, and therefore only specific discrete energy levels, are allowed for the electron. It's the wave needing to fit that forces the energy into these discrete steps.
Wow. Okay. That's the aha moment, I think. The energy levels aren't just some arbitrary rule. They're a direct consequence of the electron behaving like a confined wave.
Absolutely. It falls right out of the mathematics describing its wave nature and confinement.
Now, the analysis also mentions that an atom isn't a 1D string, it's 3D space.
Right, which makes the standing wave patterns, the orbitals, more complex than just bumps on a string.
These are the shapes we learn about in chemistry, SPDF orbitals.
Exactly. Those shapes are simply the visual representations of the different ways an electron's probability wave can form a stable standing wave pattern in 3 dimensions confined by the nucleus.
The source describes the s orbitals as the simplest, spherically symmetric.
Yeah, like the fundamental note on the string, but in 3D. The basic one's orbital is just a sphere of probability around the nucleus.
And then higher energy s orbitals like 2s.
They still have spherical symmetry overall, but they have nodes, spherical shells, where the probability of finding the electron drops to 0. So the 2s has like a sphere within a sphere pattern.
And the p orbitals are different, the dumbbell shape.
Right. The analysis points out they have a different kind of node, a nodal plane that cuts through the nucleus. That dumbbell shape is a more complex 3D standing wave with one of these angular nodes.
Okay, and d and f orbitals.
Even more intricate shapes, more lobes, more nodal planes. But the principle is the same. Each distinct shape is a specific, stable standing wave pattern allowed by the Schrödinger equation for that atom.
And each corresponds to a specific discrete energy level.
Exactly.
So let's pull this together. What's the bottom line here?
The bottom line is that the seemingly static, unchanging wave function of an electron inside an atom is fundamentally a stable, standing wave. Not of stuff, like a string.
But of probability.
Right, a standing wave of probability density.
And even if there's some internal wiggling of the waves phase, the pattern we can observe, the likelihood of finding the electron here or there that stays fixed in one of these specific standing wave shapes.
And this model, coming straight from Schrödinger's equation, gives us this beautiful, really fundamental reason why electrons in atoms have discrete energy levels.
It's because they are literally occupying the only wave states, the only standing wave patterns that can stably exist, that can fit within the atom's confinement.
Couldn't have said it better myself.
And thinking about it, this standing wave idea isn't just some, theoretical nicety. It underpins everything.
Oh, absolutely.
The structure of the periodic table, why atoms bond the way they do, chemical reactions, the properties of materials.
Yeah.
It all comes back to these allowed electron standing waves.
It really is the key to understanding the microscopic world, and therefore the macroscopic world, too.
Which leaves us with a pretty profound thought, doesn't it? If an electron is this standing wave of probability when it's bound in an atom, and it's like a traveling wave when it's free,
Right.
and yet we can also detect it as a localized particle, this duality, this wave-particle nature, this ability to be both a spread-out pattern and a point-like thing.
Yeah.
What does that tell us about reality itself,
Yeah.
at the deepest level?
That is the million-dollar question, isn't it? Something to definitely keep pondering.